Okay, so I'm going to skip the first slide. And I would like to talk about the Linux HT, called LinHT for short. It's a GNU Radio configurable handheld transceiver. So it's something like a Pinto SDR, but imagine that you've got a Pinto SDR connected to your laptop, and all of that is squeezed together inside a handheld radio and has 5 volts of power output. So you can do all of that. Most of what Pinto SDR can do inside a handheld transceiver. So of course, let's go to the beginning and focus on what are the options available on the market right now that we see. Those are a few radios from different manufacturers, and I have edited the photos to hide the manufacturer names because maybe in the future they are going to release an M17 radio, so I don't want to piss them off. So those are the radios that are at the market available. They are available at the market, at the retail, and most of these radios are just analog FM based on the same chips, 8046. That's one of the most abundant chips that is used in this kind of devices, this segment. And the other one is BK4819 chip, which does only FM with some support for AM and SSB, but if you want to do that, that chip has to be, let's say, hacked. So it doesn't do that just out of the box. You cannot just turn the radio on and transmit SSB. If the radio uses the beacon chip, you have to change the firmware, you have to reflash it. So it doesn't come out of the box with that kind of functionality. So that's a problem because the manufacturer manufacture these radios for the amateur radio market, and they don't care much about the needs that we have. We don't need yet another radio that looks fancy with just FM only, right? So what's the point of releasing a new radio similar to this one, but instead of being orange, make it green and add a flashlight? Is that innovation? I don't think so. So this is what happens now, and we don't like it. So let's go back 2 years to 2023. This is when we designed the OpenHT, which was our first try to design something as an alternative to whatever was on the previous slide. So this radio was supposed to be open source, and it was supposed to support not only FM, but basically virtually any mode that's thinkable, so including Tetra. And that device was supposed to be dual band. It supported 70 centimeter band and 2.4 gigahertz. So that's a very uncommon combination. But that device worked, but it never went through the proof of concept stage because it was very hard to develop for. That device was an FPGA. You can see 3 shielded compartments. The one at the top has the RF part on it, and the RF part is based on the microchip 8086 RF215. It supports some more than just 70 centimeter band and the 2.4 gigahertz, but we decided to use only these 2. Then the part in the middle is the FPGA. That's where all of the bad things happens there, because it's very hard to develop for an FPGA. You are not forced to use the manufacturer's IDEs and the tool chains, but in our case that was necessary, because back then I don't think there was any viable replacement for that. So that was the only option, to use Lattice Radiant software suite to develop VHDL code for that beast. And then at the bottom there is the power supply. So we had to shield it because it was causing too much interference. So that was the design. It didn't work well, even though the idea was pretty noble. We wanted to design an open source radio with the support of virtually any mode. but it turned out that it's too hard to develop for. That was the biggest problem with the design. And also, due to the FPGA, yeah, the cost was very high. Okay, it wasn't super high, but it was not acceptable. So that was a problem. And then we also decided to use an STM32 development board as the front panel, as the interface, because there is an STM32 development board with a touch panel and a display with a touch sensor. So we decided to go that way. I don't have a photo showing the other side of the board. It's actually two boards sandwiched together, connected together, and the other board is the interface. No, actually, there is a photo in the next slide showing that. So the problem was that that board was, availability of that board was very limited. So that was a problem. So this is how it looks like, yeah, I just remember. At the back, there is a set of two batteries, two lithium-ion batteries, 18650, or that, I think that's the standard here. So we used two of them, and that's the front of the device. You could set the frequency, you could transmit M17, and even received, I think, and decoded M17 at some point. But, and of course, that's a 3D printed case, 3D printed chassis for the device, which I'm not a big fan of 3D printing, because Karol showed me that it can be done very neatly, but it depends on the printer that is used and the filament. So it sometimes can look really bad. So that was a problem. But the design was still open source, including the case. So fast forward to 2025, that's earlier this year. We decided to go a different route. So instead of just designing the case and the PCB and all of the internals, we decided to pick a donor radio, which in our case was the Retevis C62, which is a clone of a Cherda UV58D. Maybe it's not a clone, but it's the same radio, and I believe it has the same internals, just manufactured by probably the same company, but sold under two different names. So that was the donor radio, and we picked it because it has a nice display, and it has a USB-C connector, which is very nice because the system on module that we use allows for connection, emulating Ethernet connection over USB, which is very convenient because you can run Linux on this beast and connect to it over SSH, SFTP, to access all the files on it. You can run GCC and compile your own code in it. So that was the reason to choose this particular radio. It was not the flashlight. Yeah, so we just took the board. My wife took the photos of that board from each side, and then I aligned them pixel-wise, so they are pixel-aligned, to be able to design the board using KiCad. So that was reverse engineering. And of course, we decided to use all of the parts that were inside the radio, so we don't have to order them separately, because if you want to use this radio as a donor, you get these parts for free. They are included in the radio. So you can just desolder them and put them back on our board. Yeah, so the SDR transceiver. The previous generation of radios used FM chips only, so you can normally use FM, but if you hack the firmware, you can access AM and SSB, but only if you have the firmware. And in case of our approach, you don't need to hack anything. You've got all of that out of the box. So you turn the radio on, you prepare your own GNU Radio flow graph, you execute it, and it just works. No matter if it's Tetra, SSB, or CW, whatever. Everything just works. And the device runs Linux on a system on module, and the boot time is like 20 seconds. So we are going to improve that, don't worry. And the biggest difference is that it's very easy to develop for, because you can write Python code, you can write C code, you can compile it on the device. You don't have to prepare the image, the Linux image, every time you want to change something. So that's very convenient. You can just write code, send it to the radio over SFTP, then SSH onto the device, GCC, main.c, and that's it. And you've got your flow graph running. And of course, it supports, I think it also supports Rust, but I'm not sure about that. Yeah. Then, it's much less expensive than the OpenHT because it doesn't use any FPGAs, which is good because FPGAs can be sometimes hard to get. But the problem is that they are expensive and power consumption is significant. So if you use a system on module with an XX1255 RF interface chip, the power consumption is really low. I have measured 180 milliamps of current consumption when the device is doing nothing. Just the backlight, the display's backlight and the keyboard's backlight. Just receiving. Doing nothing. So that's really low, that's acceptable power consumption. Then the system on module that we use, the system on module that we intend to use in the next revision has a standardized footprint, which is very important if in some other release in the future we would like to change the module to something else, having different properties, like, for example, having more memory. It would be very easy to switch to a different SOM because of the same footprint, which is a standard. And of course, improve the ergonomics. Look at this radio. It fits your hand. You can put it in your pocket. It doesn't have any 3D printed parts, so it's sturdy, it's solid. And it just works. And it has a battery embedded, so there is not a problem with lithium-ion batteries sticking out the back of the device. So it's very elegant. Then this is the this is the system on module that we use currently. It uses some NXP. There is no name for it. I think it is IMX93. It's the chip in the upper left corner, I think. No, that's the other one. Lower right corner. That's the NXP SLM chip. It has a dual-core processor and coprocessor plus a floating point unit. So that makes the execution of GNU Radio flow graphs. And that's it. That's super fast because the other SLM that we have tested actually didn't have the floating point unit. So if you wanted to calculate, for example, the root raised cosine filter for the M17 baseband, it was so slow that it was not possible to run it in real time. And with this beast, it's like, shoot, and that's it. Real time. Also the drum. Yeah. 3 by 3 centimeters footprint. I can show you the board with this chip at our table later on if you're interested. This is a sample flow graph using GNU Radio for M17 receiver. It uses the M17 decoder written by me and Jean-Michel Free. So two of us a few years ago decided to provide a set of blocks for easier experimentation with M17, because GNU Radio is a great tool for that, obviously, also for DSP, because like half of these blocks do DSP. The upper part does DSP and the other part does decoding. I mean, decoding is just done by the M17 decoder, but then you have to untype the bits and then push them to the output. The output is the OptiSync ALSA, very, very nice and always always works, outside screen always works, right? Yeah. So from the baseband to the speaker, that's the path for M17. There is also a 0MQ tab at the baseband level, so you can actually debug the system and peek through peek at the baseband. So you can see if the signal is good or if the decoder is broken. If you experiment with this kind of things. Yeah. So that's M17 decoder running on the LinHT. And the best part is that you can share this kind of flow graphs designs, and you can share them with the community, which is great. You can design something, tell everyone, okay, I've done this, take a look at it, maybe it's interesting for you, you can use it. So that's great, I think, that you can share it. Now, what's the innovation offered by this device? Amateur radio is mostly based on CW, SSB, FM, and some digital modes, excluding M17, that are based on proprietary voice coders. So this actually creates a paradigm shift for the amateur radio, because you no longer have to stick to FM, because it's limiting what we can do, limiting our bandwidth to 24 kilohertz for the channel width, and limiting us to AFSK or FSK, whatever. So if you have an SDR that you can put in your pocket and transmit 5 watts with it, you can transmit anything you want, including real-time video, 2 megabits per second, links, no problem. And truly all mode. So let's say that you've got the IMPE voice coder, which is used by P25. You can implement P25 on this device. Then, if you want to go for Tetra, you can use Telife, Osmo, SP5WWP software for this. It runs on it, and you can decode Tetra traffic and voice channel traffic. If you want to use the ACELP voice coder used by Tetra, you have to go to the HC website and download the voice coder and then compile it, and it just works on this device. Just because you have the access to GCC, which is not available in any other radios. Then, one of the best parts is that the system on module actually has a neural processing unit that has the capabilities to use what Felix is working on. And we believe that it's going to revolutionize amateur radio by giving a better quality of sound, of speech at the handheld level. Because maybe if you remember what Felix said, that neural networks, decoders for the speech, they are very computationally expensive. So you cannot run them. I mean, maybe you can run them on Raspberry Pi 5, but Raspberry Pi 5 is slightly bigger than this radio, I think. It wouldn't fit inside at least, right? So if you wanted to run whatever Felix come up with, let's say after 6 months from now, you can probably run it on the NPU, because it has a TensorFlow light support. So that can considerably increase the voice quality of codec 2 being decoded. And of course, easy RF protocol development, because you can just put some blocks together in GNU Radio, transfer it to the radio, compile it on the radio, and then just run it. In the demo code, we've got a directory with different flow graphs, and you can select them using the up and down buttons, and then execute them using the upper left button, the green one. And then you've got FM, Tetra, and M17 coder. That's what we have now. Yeah, so I also tested the 2 megabits per second links. This is not 2 megabits, this is 1.5 megabit using 64 QAM, and that's the signal transmitted by the LinHT, the one that I have at the booth. And this signal was solid enough to be decoded by a signal analyzer that I happen to have. So it works. It synchronizes There is not much error at the constellation. The error vector magnitude is very low, so I think that's a pretty solid solution, even though we use a standard TXCO part inside the LinHT of the transceiver. The current draw, yeah. So at idle, it's about 180 milliamps. At 7.4 volts, that's 2S battery. That's the standard voltage of a 2S battery. And with the M17 reception, we've got 0.2 amps of current draw at M17 reception. So that's not much. It's not much more than the idle current. Now the cost of the prototype. This is the cost that we had to pay for a series of 5 prototypes, and the most expensive part was, of course, the system on module, because if you buy 1,000 pieces of them, the cost is like $32 US per piece. And if you buy just 1 or 5, the cost is like 70, 72 or something. So it's very expensive if you buy low volume. So that was the total cost for 5 pieces, but only $1 included. So I didn't need $5. I just wanted 1, but I ordered 5 sets of the PCB. And many people asked me before, including LinkedIn, if the device runs Doom. Yes, it runs Doom. Of course, the resolution is very limited, so it's not going to look very nice, and the control is not going to be very convenient, but it does. It does. Yeah. The device runs Doom. So further reading, you can scan the code, and that should lead you to some more documentation behind LinHT. And I hope you had a good time listening to what I had to say about our new revolutionary device that we are working on. Thank you very much.